Em primeiro lugar, eu queria saber se eu vou falar em inglês ou em português. Do you understand Portuguese? Not much. Ok, então acho que a regra diz, se tem uma pessoa que precisa do inglês, a gente vai mudar para o inglês. Tá bom? Alguém tem algum... Alguém não entende inglês? Ok. Quem cala consente. Okay, so this is the first day of a sequence of lectures that we are going to talk about Ratner's theory. So this is part of the thematic semester, Dynamics Beyond Uniform Hyperbolicity. In this first month of August, organized mainly by, the responsible of the month is Gugu. And there are some other organizers that are helping him to organize the month. We are going to have 2 mini courses, and after these 2 mini courses, we are going to have 1 workshop. So the mini courses are going to be, the first one is going to be on Ratner's theory, and here is the schedule of the mini courses. So we're going to have 6 lectures. All of them will be from 3:30 to 5 p.m. And the first 4 lectures I will give them. And the last 2, Alex Eskin will give them. So the idea is that I will introduce the background and some simple examples and notation, and then Alex Eskin comes and tries to give you an idea of the proof of Ratner's theorems in some special cases, some simple cases. Okay, and at the same time next week, we're going to have the beginning of the other mini course, which is going to be in Ergodic Ramsey Theory. And it's going to be given by Vitaly Bergelson. So note that there will be a difference of time, so it will be from 5:30 to 7:30 p.m. Okay? So these 2 mini courses will be given in the next 2 weeks, and after these 2 weeks we'll have a workshop. So let me also put here, workshop. Which will be from 19 to 23rd of August. Okay? Who didn't register in the website should register. And, okay, during the workshop we will also have a Magna talk of Elon Lindenstrauss. So actually he will give 2 talks in this week of the workshop. One will be the Magna talk and the other one will be the talk itself of the workshop. Okay? So, yeah, that's right. So in here he'll give 3 talks. The third one will be at UF, but do you know when it will be? I don't know. 15. So it will be next week actually, right? Yeah, next week. So next week we have 1 talk, and in the workshop you have 2 talks. Good. So what we are going to talk about is, what we are mainly focused on is on Ratner's theorems. I want to show you and to make you understand the statement of Ratner's theorems. After doing that, I intend to give a few, the most basic examples of applications of Ratner's theorems, which are horocycle flows on hyperbolic surfaces. So in order to talk about horocycle flows in hyperbolic surfaces, we have to talk first about the hyperbolic plane. So this is the first lecture that I'll give today. Half of it will be focused on the hyperbolic plane and its properties. And the second one will be focused on the way that you go from the geometry to the algebra and how to interpret these geometric entities, the geodesic and the horocycle flows, as flows on quotients of Lie groups. Okay? So let's start. So what is the hyperbolic space? I guess most of you have seen it before. So topologically, it's just the upper half plane. So it's the set H of z equals to x plus iy belonging to C, such that Y is positive. Okay? This is the hyperbolic space. You can see it also in another geometric model, which is the Poincaré disk. But I will be focused mainly, most of the examples we will see on the upper half plane. So this is the hyperbolic space. And why the name hyperbolic? I mean, hyperbolic. In principle, it should be, it has zero curvature because it's inside R2. But what is interesting is that we can introduce an inner product different from the Euclidean one, which gives this manifold, this space with this inner product, curvature equal to -1. So the definition of the inner product is the following. If you have two vectors in some tangent space of a point Z of the hyperbolic plane, you define the inner product, let's say the hyperbolic inner product of these 2 points. It is a multiple of the actual inner product of R2, and the factor that you multiply by is the imaginary part of the basis point to its square. Okay? So first of all, it's well defined because if Z belongs to the hyperbolic plane, then Y is positive, so you're not dividing by 0. Okay? So as you see here, the hyperbolic metric is conformal to the Euclidean metric. So if you have any isometry, which we will see in the future that we have plenty of them, these isometries should preserve angles. Okay? So this is the first observation. And this space with this metric gives us a manifold of dimension 2. It is a complete manifold. And what else should I say about this manifold? So this guy is complete. Yeah, just this. Which means that among 2 points, I mean, you can extend infinitely any geodesic. The geodesic is defined on its whole domain, which is the real numbers. Okay? So this guy is complete, and by saying that, I say that geodesics can be extended. But what are the geodesics? I mean, let's see what are the geodesics. And the way that we will do here to check what are the geodesics is by checking what are the isometries. Because we know that isometries, they should send geodesics to geodesics. So if you have plenty of isometries, you can get only one geodesic and then start to apply these isometries and get many other geodesics. So before proceeding to the geodesics, let's see what are the isometries of the hyperbolic space. So they are the Möbius transformations. And in order to introduce the Möbius transformations, I'm going to introduce this group here, which we will work a lot in the next days. It is the special linear group of dimension 2, and it is the set of matrices, 2 by 2 matrices, each entry of them belonging to the real numbers, and the determinant is equal to 1. Okay? We call it we'll just call it SL2R. I mean, it's the special linear group of dimension 2 over the real numbers. So, what is interesting is that if you have an element here of SL2R, then you can define a fractional transformation in the complex numbers, which I'm also going to define it by G, denoted by G. But the way that I will write G acting on a point is G dot Z. And what I will do here is just consider the fractional expression given by the coefficients of G. So here I'm assuming that G is equal to A, B, C, D. So assuming that G equals A, B, C, D. So if you get a matrix of SL2R and you consider this expression, it defines, of course, it defines a map on C. But what is special about it, because it has determinant equal to 1, is that if you restrict it to H, it sends H to H. So G restricted to H sends H to H. So from now on, actually, I'm going to denote this restriction also by G. Denote it also by G. So, thus, for each element of SL2R, there is a map which goes from H to H. Okay? So for each element of SL2R, I have a map like this. And they are very special in the sense that if you calculate here the inner product generated by these guys, I mean, you consider the action of these maps. These maps are differentiable, so you can apply the derivative of it to tangent vectors. And if you have two tangent vectors and you apply G to these two tangent vectors, and you calculate the inner product with respect to the inner product with respect to this metric here, they are the same. In other words, each G of this is an isometry. So this is a simple lemma that I won't prove. You can find it on the lectures. That G is an isometry of H. That is, if you calculate, let's denote by this, dg of V, dg of W, where V and W are two, so this is applied in GZ. And if you calculate VW in Z, for VW in the tangent space of Z, these two guys are the same. Okay? So this gives us a lot of symmetries of our space. I mean, you have a manifold, and the symmetries of the space, we call them isometries. So the lemma says that we have a lot of isometries, because for each of these guys you have one such fractional transformation. And actually these guys here, from now on, I'm going to call them Möbius transformations. So each such fractional transformation will be called Möbius transformation. Let's write it here. So from now on, G from H to H is called a Möbius transformation. Okay, and let's denote this set of Möbius transformations by Möbius. Okay? By the lemma, every element of the set is an isometry of H. Okay? But the set itself, it has a structure on it, right? Because if you have two transformations, you can compose transformations. So Möbius, you can see the set Möbius as a group. And also SL2R is a group itself. And this map that you associate an element of SL2R to a Möbius transformation, you can easily check that it is a homomorphism. So I'm going to leave it as an exercise to check that the map that sends G from SL to R to the, let's say, the map, the map's transformation G associated to it is a homomorphism. Okay? So what does this mean? This means that if you get two matrices G and H, then you have two maps defined. You have the map G and you have the map H. So you can consider the composition of these two maps. You get a point on the hyperbolic space, you apply H, and then you apply G. But you also have that if G and H are two matrices in SL2R, the product of them is also a matrix of SL2R. And by this map, you can induce a Möbius transformation associated to GH. And if you are a Möbius transformation, you are a transformation acting on H. So you can also consider the point DH, GH, of Z. This gives a new point of H. So what the exercise tells us is that these two guys are equal. Okay? So you have a group homomorphism between SL2R and Möbius transformations. Okay? Okay. So okay. A fact is that Möbius transformations, they are the set of all orientation preserving isometries. By the lemma, they are isometries. And by this observation, they are all the orientation preserving isometries. There is only one map, there is only one isometry which is not orientation preserving that cannot be a Möbius transformation. I mean, if you get this other transformation, which now I don't remember what it is, and you consider the subgroup generated by this transformation and Möbius transformation, this gives you all the isometries of H. Reflection, okay. So this other guy is reflection. Reflection does not preserve orientation, so you get all the isometries. But we won't work with reflection. Let's focus on Möbius. Okay, so now that we know that we have a lot of isometries, let's see what are the geodesics of our hyperbolic space. So geodesics of H. I'm going to start with only one geodesic. So, what defines a geodesic? A geodesic is defined by a point and a direction, right? And a vector. So, let's fix one of these guys. So, let's say that we fix the basis point to be I and this direction to be pointing upwards. So, actually, I'm going to fix a vector, which I'm going to define by I. And this vector is a unit vector tangent at the point I of the hyperbolic space. So if you have the drawing here of the hyperbolic space, you are in this basis point, and the vector you are considering is this. Okay? So, a fact is that the geodesic defined by this vector I is the y-axis. Okay? So this is a fact. It is easily checked. I'm also going to leave it as an exercise. But what it allows us to get is that once you have this one geodesic, you can start applying the isometries of the space and getting other geodesics. So what are these guys? So if we apply Möbius to this geodesic, we get geodesics. To this geodesic, yeah, we get geodesics. And we know that because the metric, the hyperbolic metric, is conformal to the Euclidean metric, as I said in the beginning, Möbius transformation, they should preserve angles. So the image of a line like this, which is orthogonal to the x-axis, should be also orthogonal to this x-axis. And it is not hard to see that the images that you can get are like this. They are semicircles, which are orthogonal to the x-axis, or they are vertical lines, which of course are also orthogonal to the x-axis. Okay? And if you run over all the possible Möbius transformations, you run over all the possible geodesics, and this is going to give all of these such semicircles and all of the vertical lines. Okay? So the geodesics of the hyperbolic space are semicircles or vertical lines, which, if you want to see vertical lines as a semicircle passing through the point at infinity, then all the geodesics of H will be semicircles orthogonal to the x-axis. Okay? So, in the model of the Poincare disk, there will be actually no distinction between this guy and this guy. So in the model of the Poincare disk, the geodesics are going to be such, they are not semicircles, but they are arcs of circumferences, which are orthogonal to this guy here. And they are, when this degenerates here, they become a straight line. So these straight lines are related to these lines here, and these other guys are related to these other guys here. Okay? So these are the geodesics of H. And these are the geodesics of H in the Poincare disk model. Good. Okay, so we have this hyperbolic space. It's very nice. It has a lot of isometries. And it's actually universal in the sense of hyperbolic geometry. And by this, I mean that if you get... So this is what we call hyperbolic surfaces. And what is hyperbolic surface is a surface if it is a manifold of dimension 2, which is complete and orientable. This is what we call hyperbolic surface. And actually the hyperbolic plane gives rise to all hyperbolic surfaces. I'm sorry, and of curvature equal to -1, which is complete, orientable, and has curvature equal to -1. Okay, so the hyperbolic plane gives rise to all of these hyperbolic surfaces. Why? If you have X like this, with these three properties, if you apply the Riemann uniformization theorem, you get that the universal cover of this guy should be H. So if X is hyperbolic surface, then its universal cover is H. So if you look at the deck transformations, the deck transformations will be a subgroup of the isometers of this guy. So it will be a subgroup of the isometry of this guy, but it will be also orientation preserving because the surface is orientable. So if you have orientation preserving subgroup of the group of isometries, this means that you have a subgroup of the Modulus transformations, right? And once you have the deck transformations, you can consider the quotient of these guys to get back your space. So if X is a hyperbolic surface, then its universal cover is H, and gamma, which is equal to deck transformations, is a subgroup, a discrete actually, of the set of Möbius transformations. Okay? So I won't delete this. So you have this, and furthermore, you have the quotient of this discrete subgroup, which I'm going to denote by gamma, subgroup gamma of by this deck transformation subgroup, you can recover the hyperbolic surfaces by applying the quotient. Okay? So I'm always going to consider right quotients, and we are going to see in the future. At least I prefer them, but I also am going to convince you tomorrow that there is no distinction between right and left quotients. Okay, so what do I want with this discussion? What I want with this discussion is that the hyperbolic plane is very special, and it actually gives rise to all of such objects like this. So if you want to do geometry in constant negative curvature, in some sense what you have to consider is subgroups of the Möbius transformations. Okay? Good. So I don't know if I'm going too fast or too slow. Do you have any questions? I don't know if you are familiar with these things of hyperbolic geometry. So who is familiar with these things that I spoke so far? Two guys? Sérgio, no? Okay, so let's keep going slow. So let me see what's next. Okay. So a summary from now is that we consider a space. Actually, it's a surface. It is not compact. It has curvature equal to -1. We know who are all the isometries of this surface. There are plenty of them. We have a lot of symmetries of this space. We know who are all the geodesics of the surface. They are easily described from the Euclidean perspective. And we know that this surface gives rise to all other non-simply connected surface. I mean, if you get anything you can construct from this special space H. So let's start to do dynamics on this space. For now on, we only saw the geometric point of view. So to start to do dynamics, I mean to consider the geodesic flow. Which I'm going to denote by G. I don't know if this is good. That's okay. Okay, so what is the geodesic flow? The geodesic flow is a flow, but it's not a flow on the manifold itself, right? It's a flow on the tangent bundle of the manifold. And actually we know that geodesics, they preserve norm. If you walk on the geodesic, you have the same length of the vector. So actually, the geodesic flow should be restricted to some submanifold of the tangent bundle. And for simplicity, we are going to consider the unit tangent bundle. Okay? So the geodesic flow is a flow on the unit tangent bundle of our space. Okay? And what does it do? It picks a vector v, and it walks. So the time t of this flow, what it does is to walk a distance t along the geodesic that this vector defines. So you are here. If you walk t on this direction, you follow here. Okay? So if gamma is a geodesic such that gamma prime of 0 is equal to v. And by here, I mean two things, that the basis points are the same, and the vector, the speed vector that it defines is v. So if gamma is a geodesic such that this happens, then the geodesic flow, which I'm going to define gt, what it does to v, it walks t on the direction of the geodesic, and it looks at the vector that's defined by this time t. Okay? So this defines a flow g equals to gt for t real. Okay? So as I said, the inner product that we define, it makes the hyperbolic space to be complete. So if it is complete, this is actually a flow defined for all real times. Okay? And what is a flow? It is a flow in which sense? It is a flow in the sense that that if you compose two such guys, you just sum the parameters and you get the composition. Okay? It is a flow like this. Okay. So, but what happens to this flow? You have here the hyperbolic plane, and you have some vector v. So what you do, you look at the geodesic that the vector defines, and you walk t along this geodesic. This guy is not interesting. Why? Because if you keep applying if you apply the geodesic flow for large times, then it's going to converge to this point here, right? It's going to die on this point at infinity. And if you apply to negative times, it's going to die at this point at infinity. So this flow has no recurrent properties. It doesn't have closed orbits. It doesn't have anything. Everything is very simple. It's like South Pole, North Pole. In the future, you go to a point. In the past, you go to a point. Of course, this point, it changes if you change the vector, but nothing goes on here. The situation changes if instead of considering the geodesic flow on H, we consider on such quotients here. Okay? So, just to summarize, the geodesic flow on H is boring. But the geodesic flow on X equal to gamma mod H is boring or not. Okay? So the identifications that you make with this group of isometries here allow you to come back to where you started, for example. So for example, if you have a space which is called the Modulus Surface, and it is something like, I'm going to draw a fundamental domain. In the next talks, you are going to see why this is a fundamental domain, and actually what is a fundamental domain. So you have this space here. So if you get the geodesic flow on H, you have something like this. You have a point here, a vector, and you walk like this, and you die here, and you are born here. But if you consider the geodesic flow on this quotient, which has this fundamental domain, once you are here, you enter in the fundamental domain, but when you come out of the fundamental domain, you should consider the identifications that you get to define the space. So actually this vector here, it defines a new vector which goes something like here, because I identify this with this. And this new vector should be something like this. And you keep walking on the direction now, not of this vector, but of this vector. So you do something like this. So again, you fall out of the fundamental domain. So you should consider the new identification. You send this vector to a vector right here. Okay? And like this, you can continue. So once you consider quotients of H with these discrete subgroups, then you can have recurrent properties of this geodesic flow. Right? And this is more or less what you're going to deal with. Good. Okay. So if you are from dynamics, you have heard that the geodesic flow on negative curvature is a nozzle. And by this, we mean that there is a stable manifold. It's a set of points for which the future is the same. And you have an unstable manifold, a set of points for which the past is the same. And we are in the situation that we have negative curvature, right? So we should have stable and unstable manifolds. And what are the stable and unstable manifolds for the geodesic flow, for example? So this is what we call the Horo cycles. So the next topic that I'm going to talk about is the Horo cycle flows. So this we checked, this we checked, this we checked. Good. So the Horo cycle flows, I'm going to put H plus and H minus. So as I said, G is in a nozzle flow. It has stable and unstable manifolds. You contract on stable, you expand on unstable. Okay? So the question is that, what are the stable and unstable, let's call them leaves. The stable is what we are going to call the stable Horo cycles, and the unstable Horo cycles. And now I'm going to describe them to you. So to describe them to you, again, let's pick a special vector and try to check what happens with this vector. So the vector that we are picking is no longer here, but is the vector I. Is the vertical vector, unit vertical vector at the point I. Okay? So let us describe the stable set of this guy I. So we have here the upper half plane again, and we are fixing this vector here. Okay? So the stable set is the set of vectors for which the future under the geodesic flow is the same as the future of this guy here. But what is the future of this guy? Well, we walk on the geodesic. And to walk on the geodesic, you just translate this point upwards, right? Because you know that the vertical line here is a geodesic. So if you any candidate for an element of the stable set should also be vertical, because it should be also going upwards. And actually, you can check that this set is defined as follows. You consider the horizontal line passing through this point I here. So this is the line for which y equals to I. And you consider all unit vectors centered on these points of this line. Okay? So you have unit vectors here. And they are really unit vectors in the Euclidean metric, because if you are on the line, so y here is equal to 1, I'm sorry. If you are on the line which y equals to 1, when you look at the metric is the same as the Euclidean metric. So the distance of unit vectors in the hyperbolic metric is 1 in the Euclidean metric. Okay? So this constitutes the set which I'm going to call the stable set of I. So these guys here are all the vectors I belonging to T of x plus I, where x runs over the real numbers. Okay? Okay. So this is the stable set of this guy. So what are the other stable sets? What do we do to get them? Again, we apply isometries, right? Oh no. Well, let's see. So let's see what happens if you have a vector here. You know that this vector, you know where exactly the vector is going to die. So you should draw the geodesic, and it's going to die here, right? So any point on the stable set of this vector should also die here. Correct? And we can actually draw what is the horocycle, which is the stable set of this guy. It's going to be vectors which are orthogonal to the circle that I drew here. And what does the circle do? It passes through the base point of the vector, and it's tangent to the same point at infinity that the vector converges to. So if you look at all unit vectors with bases on these guys here, this is going to constitute the horocycle, the stable set of this vector. You can actually see that by Euclidean properties, if you consider the geodesic that passes through this guy, the geodesic is going to die here. Okay? And actually they go to this point with the same rate. I mean, they really approximate to each other. This guy and this guy, if you apply the geodesic, they all converge here, and the distance between them is going to decrease to 0. So the conclusion is that stable sets are of two kinds. It depends whether the vector is vertical pointing upwards or not. If this vector is pointing upwards, then you have horizontal lines. If it's not vertical and pointing upwards, then the horocycle is going to be some vectors which are orthogonal to a circle which is tangent to the x-axis. Okay? So these are the stable sets, which we call the stable horocycles. The sets are called stable horocycles. So we did for the future, we can do the same for the past, and this defines analogously. This defines unstable sets are called unstable horocycles. Okay? Remember that from the dynamical perspective, what is the stable horocycle? Is the set of vectors W of unit length, such that when you consider the geodesic flow of the basis point and the geodesic flow of this other point, this distance goes to 0 as the time t goes to plus infinity. And analogously, the unstable horocycle is defined by the vectors which have unit length, but for which the distance goes to 0 if you look at the past. Okay? So I described it to you what are the stable horocycles, and to describe the unstable horocycles we can apply similar arguments and conclude that they are the following. So you have two cases. The first case is that if your vector, and let me remember, is pointing downwards. So if your vector is pointing downwards, the horocycle that it defines is also all the other vectors on the same horizontal line pointing downwards. If not, if you have any other vector which is not vertical and pointing downwards, so the horocycle that it defines, to see this horocycle, what you do first is you consider the circle which passes through it and its tangent. Oh, it gave me exactly tangent here. And its tangent to the x-axis. And with bases on this circle, you consider the unit vectors orthogonal and pointing upwards this circle. So these are the... So to make it more accurate, when you go down, your y decreases, so 1 over y square increases. So to draw them in the Euclidean metric, you should draw them smaller. So it goes smaller and smaller. Here should be actually bigger than this one, because we are with a bigger y. And so on, okay? So we know what are the stable and unstable sets, and they are both one-dimensional. So we can define flows on these leaves. So what do? We consider the leaves themselves and we parameterize them by arc length. And once you parameterize them by arc length, we can consider the flow that at time t walks a distance of t along these curves. So the stable horocycle flow is, so let me write it better. If we parameterize each stable set, stable leaf, by arc length, then we define a flow on the unit tangent bundle of H and I'm going to define this flow by H plus and I'm going to call it the stable horocycle flow. Okay? And of course I can do the same for the past. Analogously, we define the unstable horocycle flow which I'm going to define by H minus which is this guy. Any question? Okay. I don't know if no question is good or bad, but it's good or bad, no questions? Not even this you can answer?
When you say arc length, you mean hyperbolic length?
Yes, hyperbolic length, yeah. Everything here, it's intrinsic to the hyperbolic metric. So you define with respect to the hyperbolic one. Okay, so we have three flows, G, H plus, and H minus. G is an nozzle flow. It has dimension, the stable leaves have dimension 1. If you parameterize them by arc length, you define a flow on the stable leaves. Is H plus. The unstable leaves also have dimension 1. If you parameterize them by arc length, you get H minus. Okay? Good. So this is the geometric perspective, and we begin to do dynamics. So now what I will do is to try to see these three flows in an algebraic perspective, to try to represent them by a more explicit description. Okay? And this is the second part of the talk, which is the algebraic description of G, H plus, and H minus. So actually we indeed began with this algebraic description when we considered Möbius transformations as coming from SL to R. So in order to do this algebraic description, SL to R appeared naturally when we consider isometries, and algebraic description should also take into account the isometries, and is going to take into account SL to R. So first what I'm going to do is to consider the group SL to R, and write down here some of the properties of this group. So, as I wrote before, SL to R, just to remind you, is the set of all 2 by 2 real matrices of determinant 1. So these guys belong to GL to R, such that AD minus BC equals to 1. And it has some interesting subgroups which are going to be important for us. So one of them is the rotation subgroup. Which is given by these guys. These are the rotation matrices, right? So as you can see, the determinant is 1, and if you consider them as acting on the real plane, they act by rotation, right? So this guy here, what is the dimension of this guy? I mean, I have only one parameter, so it's one-dimensional. And it's actually compact because if you go from theta to 0 to 2 pi, you get everything that you could. And then you come back. So this guy is actually, it is isomorphic to S1, and it is one-dimensional. It is called the rotation group. K is the rotation group. So this is the first interesting guy that we have inside SL2R. It is a subgroup of SL2R, of course. Another guy which is of interest for us, and we are going to see that it's intimately related to the geodesic flow, is the diagonal group. The diagonal group is given by matrices of this type here for A positive. Okay? So again, they have determinant 1. If you look at the linear action on R2, they are hyperbolic matrices. And it is one-dimensional, and it is isomorphic to R, I think. Yeah, if you consider this guy and you associate this guy to log of A, then you're going to have a group isomorphism. Either log of A or e to the A, I don't remember now. Log of A. Okay, so A is called the diagonal group. And we have two other guys, which is U plus, and it's given by these parabolic matrices here. And similarly, we have U minus, which is the transpose of this guy. Okay? So these two guys here, they are again one-dimensional. They are isomorphic to R. And we call them the unipotent groups. So as I told you, A is going to be related to the geodesic flow, and you should guess by the notation here that U plus is going to be related to H plus, and U minus is going to be related to H minus. And this is what we aim to do in the next half an hour of the talk. Okay, so but a few things. Most of the things that I'm going to speak now about the linear and hyperbolic action, I'm going to leave it as an exercise. I think the details are in the lecture notes. So SL2R is a subgroup of 2 by 2 matrices. So naturally it acts on R2 by linear transformations. So this is what I call the linear action of SL2R in R2, which is to each guy here, that each guy here defines a linear map in R2, right? And just to give a few examples, how does K act? How does K act? So K acts by rotation. And now you can see the reason of the name rotation group. A acts by hyperbolic transformations. And what does U plus do? So if you get an element of U plus and you apply to a vector xy, So what you get here is x plus by and y. So it depends whether y is 0 or not, because if y is 0, this vanishes, right? So if y is 0, for example, and if you are applying the guy to the x-axis, like this, y is 0, so you fix all vectors of the x-axis. So it fixes the x-axis. If y is not 0, then as you run over b, you get everything here. So it translates the horizontal line that passes through y. So I'm going to put ux by... It does not act by translation, but it preserves horizontal lines. Okay. In the lecture notes, I have a few other properties of these guys, but I'm going to describe them only when we need them, in the sequel of the lectures. So we have naturally the linear action, but we also know that an element of SL2R defines a Möbius transformation. And Möbius transformation is a transformation on H. So we also have a hyperbolic action of SL2R on the hyperbolic space. So the hyperbolic action of SL2R in H is that an element here, it's what we did in the beginning, an element here defines a transformation in H. And this is the Möbius transformation associated to the matrix. And a few properties of these guys, for example. So what does an element of A do? So if you have an element like this, what happens if you apply it to a point Z? Well, it acts by fractional transformation. And what does the fractional transformation, how is it defined? So you get AZ plus 0, 0 plus A minus, 0 times Z plus A minus 1. So this gives you A squared Z. So it acts by dilation. It just expands the radius of the length of the vector. So thus A acts by dilation. And how does U plus, for example, acts? So what happens if you have an element of U plus? It is defined by 1B01. And what happens if you get this guy and you apply it to Z? Well, you get 1 times Z plus B over 0 times Z plus 1. So it's Z plus B. So this guy here defines a translation, horizontal translation, because we know that B is real. So thus, U plus acts by horizontal translations. But so the question that I want to ask now is it possible that, let's say I give you two points in H, can you get me a Möbius transformation that sends one point to the other? Yes or no? Yes or no? A guess? No guess? So the question that, in other words, the question that I want to ask is, does SL2R act transitively on H? If you consider the hyperbolic action of SL2R via Möbius transformation, is it possible that if you give me 2 points of H, can you get me a Möbius transformation that sends one point to the other? Well, just with these two properties that I wrote here, how A and U plus act on H, you can get the conclusion that the answer for this guy, for this question, is yes. Because how do you do to send, for example, to get this, I can fix one of the points. I have 2 points. Let's say that one of the points is I. If I can show that I can go to anything, then anything can go to anything. Just goes to I first, and then from I to this other point. So yes. So fix I, and let V be equal to X plus IY, another point of H. So if this guy is a point of H, then this guy here is positive, right? So I'm just going to describe you two transformations such that the composition of them sends I to this vector V. So first of all, I get I, and I apply to it the Möbius transformation associated to this matrix here. So this matrix is an element of A, and it acts by dilation. I put the square root of Y. I can't do that because Y is positive. So this point I goes to YI. Okay? And now I want to send YI to X plus YI. So what do? I can apply a horizontal translation by an element of U plus. So I get this and I apply UX01, and I get X plus YI. Okay? So I can send I to any other point. Reversely, I can send any other point to I. By composing these two arguments, I can send any point to any point. So the action of SL2R is transitive on H. And it's actually, there are many such transformations that you can do this. For example, fact K is equal to the stabilizer of I. What do I mean by this? I mean that when I get matrices that belong to K and I consider the Möbius transformation associated to it, all of this transformation, they fix I. And it's an easy task to check that. So in principle, the transformation that sends one point to the other is not unique, right? If it was unique, then the unique transformation that would send I to itself should be the identity. But we have much more than that. So, in other words, the action of SL2R in H is far from being simply transitive. And what I mean by simply transitive is that there is only one transformation, given 2 points, there is only one transformation which sends one point to the other. It is transitive because such transformation always exists, but we have plenty of them. But not everything is lost because we are not actually interested in H, right? We are considering geodesic flows. So the object, the space we are interested in, is the unit tangent bundle of H. So the unit tangent bundle of H has dimension 3. Why? Because H has dimension 2. And also this space here has dimension 3. So there is a chance that the action of this guy on the unit tangent bundle is simply transitive. And why does this guy act on the unit tangent bundle? Well, we know that every such guy here, when you look at the hyperbolic action, when you look at Möbius transformations, it is an isometry. So if it is an isometry, it preserves the length of vectors. So if you get a vector of unit tangent bundle, the image of this vector under the derivative action of elements here should also have unit length. Okay? So now I'm going to consider so just a conclusion here, that this implies that the action is not simply transitive. I have 20 minutes. Okay, so now let's go to the action of SL2R on the tangent unit tangent bundle of H. Okay? So as I told you, naturally, via the derivative, SL2R acts on the unit tangent bundle. So the question that I want to ask is the same as that one. This such action is transitive? Yes or no? So, to answer this, translating this question, the question is, give me two vectors in this space here. So give me two tangent vectors which have unit length. Can you get me an isometry, orientation preserving isometry, so an element, a Möbius transformation, that sends one of these vectors to the other? Again, the answer here is yes. And again, to proceed to the proof, we can fix a reference vector. And the reference vector that we're going to fix again is the vector I based on the point I. So fix I and let V be any other such guy here. Let's say that V is based on this guy Z. Okay? So what do we have to accomplish here? First of all, to send V to this guy here, we have to send Z to I, right? Or reversely. No, not reversely. To send V to this guy here, we have to send Z to I. And of course, we have to send the vector itself to the vector pointing upwards. We know by this question here, which the answer is here, that we can send I to anything. And reversely, you can send anything to I. Right? So there is a composition of these transformations that sends Z to the base point I here. So consider G such that it sends the base point to what we want, G of Z to I. So now, when you consider the action of the derivative, what you have here is that you started with V, and if you apply the derivative of this map to V, this guy is a unit vector tangent at the point I. Okay? Because the base point was sent to I. So, to conclude, we just need to find some other transformation which sends this new vector, which I'm going to call it W, to point upwards. And part of this fact here that I should have written here, that K is the stabilizer of I. Furthermore, it acts by rotation. It is not a rotation in the natural sense that if you have an element of K which is defined by the parameter theta, the transformation is going to be defined by theta, the rotation is going to be defined by theta. But it rotates vectors. So it rotates vectors of the tangent space at I, and it does that transitively. In the sense that if you give me two vectors, both tangent to I can get you a transformation of the rotation group that sends one vector to the other. Okay? The transformation fixes I. So the derivative action of each of these transformations is an action of the tangent space. So when you have this fact, you can just pick such k such that when you consider the action, derivative action of k on this guy w, you get the vector I. Okay? So this gives you that. Give me any vector, I can construct a transformation that sends this vector to I. Okay? So the answer is yes to our question. And again, I ask you, is it true? So let's just to conclude here. Does the derivative by the chain rule of kg applied to V is equal to I? So I got a guy. I concluded the existence of a Möbius transformation for which the derivative action of the Möbius transformation on the initial vector V is equal to I. Okay? The question now is whether this kg, so is kg unique? So is the action simply transitive? Well, not really, because, so here's the question, here's the answer, no, because if you consider the Möbius transformation which is generated by the identity and minus the identity, the Möbius transformations are the same. Right? What is the Möbius transformation associated to the identity? It's the identity. It's 1 times z plus 0 over 0 times z plus 1. This is z. And the same happens if you get minus 1, 0, 0, minus 1. It's minus 1 times z plus 0 over 0 times z minus 1. So this gives you z. So you have two transformations. Have two transformations on SL2R which give you the same Möbius transformation. So you don't have uniqueness of the guy here. Right? But this is the only obstruction. So the fact that plus identity and minus identity give the same guy restricts us to ask now, okay, let's not consider the action of SL2R itself, but the action of PSL2R. So PSL2R is the space SL2R divided by the identification of plus and minus. Okay? And this is a group. And by the same reason, this guy here defines Möbius transformations. Why? Just pick a representative here and consider the Möbius transformation that is defined by this representative. You can check, just like here, identity and minus identity, that if G belongs to SL2R, then minus G also belongs to SL2R, and it defines, gives the same Möbius transformation. Okay? So what is natural to consider is not the action of SL2R itself, but the action of PSL2R. So now the question is whether PSL2R, does it act transitively here? Simply transitively, actually. And the answer to this question now is yes. It's a simple calculation. I'm going to leave it also as an exercise. But in other words, what does it tell you? It tells you that if you give me two unit vectors on the unit tangent bundle here, there is only one projective special linear transformation which sends one vector to the other. Okay? So if you have in other words, we can construct a bijection between this space and this space now. How do you do that? You just fix a vector here. Let's fix the vector I. We could have fixed any other such vector. And to any other vector V, I associate V to the transformation here that sends I to this vector V. Okay? So this allows us, thus, PSL2R is the same as the unit tangent bundle of H. For example, fix a reference vector which I'm going to fix I again because I like I, and to each V here associate the element G in PSL2R such that when you consider the action of G on the vector I, it gives you the vector V. Okay? So, our unit tangent bundle, which was in principle just a manifold of dimension 3, is actually a group. You can consider it as a group. It is a Lie group. Okay? So we know that we have 3 flows defined here. Then we can see what is the description of these 3 flows in these coordinates. You pull it back the coordinates that I constructed here. So you pull it back the coordinates to PSL2R and you see how are the 3 flows defined. So I have 5 minutes. I think I need 10 minutes. So I'm going to use 4 more minutes of your time to give the description, algebraic description of these 3 flows. Oh. So G, the geodesic flow in PSL2R coordinates. Okay. So let's start with the following. By this association, because I fixed the reference vector I, the matrix which the vector I is associated is the identity, right? The identity here, if you get G equal to the identity, D of the identity at I is equal to I. Okay. So what the geodesic flow does to I at the time 0 is nothing. It applies the identity. So first, what we have to see is how is the geodesic parameterized by arc length. So look at the geodesic passing through I. And you can check that the arc length parameterization of this guy here is this. This is a curve which at time 0 passes through I. The speed vector at 0 is the vector I, and it's parameterized by arc length. If you consider the derivative and you apply the inner product that I defined in the beginning, it's going to give you 1. Okay? So, what does the geodesic flow do to a vector here? So, is parameterized by arc length. Thus, GT of I, it's again a vertical vector, but instead of having base point at I, it has base point ETI. Okay? So I'm going to define as like this, ETI I. Or even better, I'm going to define as I belonging to the unit tangent space of ETI. Okay? So what the geodesic flow does to this vector here is just sending the base point I to ETI and then send the tangent vector to a tangent vector here, unit guy here. Okay? So, if you want to see this flow in PSL2R coordinates, you have to see what is the Möbius transformation that sends this point, actually, that sends this vector to this vector, right? So I claim that the Möbius transformation that does this, and actually the matrix, or the element, someone spoke? Oh. Or the element G, PSL2R, that sends the vector I to this vector here, I belonging to the unit tangent space of ETI of H, is a diagonal matrix of this form. Okay? Well, the base point actually goes to ETI because it gives me ET over 2 I plus 0 divided by 0 times I plus E minus T over 2 gives me ETI. And because it should, it acts hyperbolically, it preserves the y-axis, it should send the vertical one to the vertical one. And you know that it is an isometry, so it should send the unit vertical vector to the unit vertical vector. Okay? So in other words, thus in PSL2R coordinates, GT of the identity, which is the vector, which is the matrix associated to the vector I, which I fixed, is this matrix here. Okay? So if you consider any other vector, and you consider and H is the element here, such that D H is the matrix associated to V, in the sense that it is the matrix that sends I to V. Then, if you look in PSL coordinates of the element H, what does the geodesic flow do to the element H here? Is basically the same. It gets the matrix H and it multiplies on the right by this. Okay? So, in other words, the geodesic flow can be described as a flow in the Lie group PSL2R. And what it does is to get one matrix of PSL2R and multiply on the right by this diagonal matrix here. Okay? Is the geodesic flow in PSL2R coordinates. Good? So, we are almost there. We just need now to get the description, the algebraic description of the horocycle flows. So again, I'm going to fix this reference vector and to see how I apply the horocycle flow to it, to get what is the matrix that sends the vector V to the image of it under the horocycle flow. And it's going to be a multiplication by this matrix And by analogy, if I get any other vector here, the horocycle flow is going to define by a right multiplication, but now by another matrix, which is not this one here. Okay? So the H plus and H minus in PSL2R coordinates what is it? So again, get the reference vector I. We know who is the stable leaf of it. It's all the unit vectors pointing upwards with base point on this horizontal line. Okay? And because they are all on the horizontal line for which y is equal to 1, the metric, the restricted metric here is the same as the Euclidean metric. 1 over 1 squared gives you 1. So, when you parameterize that by arc length, what you get is that when you walk t on the direction of the horocycle flow, you walk t on the Euclidean metric as well. So what it does is to send the vector I to a vector which is again pointing upwards. It is unit vector in the Euclidean metric, but now instead of having basis on the point I, it has basis on the point t plus I. Okay? So we have that h plus t of the vector I is equal to the vector I, but now with a different basis point, t plus I. And who is the matrix? The element G, not G, but let's call it H. The element H, not H, let's call it U. The element U that sends I to this new vector I belonging to T1 T plus I H is, I claim that it is this matrix here 1 T 0 1. Upper triangular matrix where the T is here. Why? You just need to check the basis point, right? So if you get 1 T 0 1 and you apply it to the vector I, so what you get is 1 times I plus T over 0 times I plus 1. So what you get is T plus I. So if you fix the basis point, also the vector should go to the vector here. So in PSL2R coordinates, the horocycle flow acts as multiplication by this matrix here. So if you proceed analogously as we did before, so proceeding analogously, then you can represent the horocycle flow, stable horocycle flow in PSL2R coordinates as follows. So actually I'm going to consider a matrix like this. A, and you get the matrix A, you multiply it by this matrix 1, 0, T1. Okay? If you do the same for the unstable guy, you get the matrix and you multiply it on the right, but not by this matrix, but by its transpose. So you get 1, 0, T, 1. Okay? So in PSL2R coordinates, geodesic flow is multiplication on the right by a diagonal matrix, by a hyperbolic matrix. Stable horocycle flow is multiplication on the right by a unipotent matrix. That's what we define, the unipotent subgroup, right? U plus. And also the unstable is by a unipotent matrix, a different one, but again, unipotent. Okay? So I ran out of time, and we still had one guy to discuss about here. So let me just make a conclusion that is to compare geodesic and horocycle flows, at least on hyperbolic surfaces. So as I said before, geodesic flow is a nozzle, right? So instead of considering geodesic flow on PSL2R itself, so the geodesic flow on the space H, we could consider on quotients. So if instead of considering the whole space, you consider the quotient like this, then the geodesic flows that we induce, well, if X is like this, the tangent space of X is gamma mod the tangent space of H. So that the geodesic flow is a flow on this quotient. But if you have an association of T1 of H with PSL2R, this quotient here is nothing but the quotient of gamma with PSL2R. So the geodesic flow of this hyperbolic surface in PSL2R coordinates should be a map from PSL2R mod gamma to PSL2R mod gamma. Okay? And it does the same thing. It gets a coset. Now it gets a coset. H, gamma H, and it multiplies this coset. It sends to a new coset, which is this product here. And the same happens for H plus and H minus on X. It's going to be defined now instead of PSL2R on the quotient. And what it does, it gets a coset and it multiplies on the right by this matrix. Okay? Okay, so now we have descriptions, algebraic descriptions of geodesic and horocycle flows on hyperbolic surfaces. As I said before, geodesic flows are anosov. So for example, they have positive entropy. They actually, if you consider a section of them, they have Markov partitions. Any time, if you fix a time, this geodesic flow is going to be a K-flow, is going to be Bernoulli, actually. Bernoulli in the sense that it is homomorphic to a full shift with a product measure. So the geodesic flow is very rich. It also has a lot of periodic points. Because it has a lot of periodic points, it has a lot of invariant measures, right? But the horocycle flow is in the opposite spectrum of this. The horocycle flow is a flow which has zero entropy, which, if this guy here, for example, is compact, if this quotient is compact, it has no periodic orbits at all. Actually, it is going to be uniquely ergodic. So geodesic flow has many of periodic points, periodic orbits, so it has many measures, invariant measures. Horocycle flow has no other invariant measure other than the volume measure. Okay? If, for example, this guy, if it's not compact but it has finite volume, it is more or less uniquely ergodic in the sense that all ergodic measures are either the volume measure or they should be supported on a closed orbit. But the conclusion is that these two flows are very distinct from each other. One is very chaotic and the other is very stable. And the reason that appears here is that the geodesic flow is a multiplication by a hyperbolic matrix. And we know that hyperbolic matrices are chaotic. On the other side, horocycle flows are a multiplication by unipotent matrices. And the property of the unipotent matrix is that instead of having an exponential behavior, it has a polynomial behavior. And this polynomial behavior is what allows the conclusion that, for example, if this quotient is compact, then there is only one invariant measure for this horocycle flow. And what Ratner's theory is about is to generalize this perspective. You have horocycle flows on quotients of hyperbolic space with a discrete subgroup, Ratner's theory deals with unipotent flows, so it's unipotent, should not be necessarily 1T01, but other matrices which are again unipotent, acting on quotient space of Lie group and lattices. So this is what we are going to see tomorrow. Tomorrow I'm going to describe the basic, let's say, the basic background to understand what Ratner's theorems are about. Okay? So I'm sorry for going over the time, but do you have any questions? I'm sorry?
If you multiply by a rotation instead of parabolic matrix or hyperbolic matrix, by a rotation matrix.
Okay.
It corresponds to a flow in H.
Well, it's going to have closed orbits, right?
Yes. Will be, but what is a flow correspond?
It's not interesting from the point of view of dynamical systems. Yeah. Any other question? Okay, so tomorrow here at the same time, at the same place, okay?